Okay, so in that last problem we were looking at, we were just thinking about, um, a car traveling with changing velocities, and then a truck traveling at a constant velocity. And for us to think about when they have gone the same distance, what we need to think about is when is the area under each of those respective curves the same. So we have this kind of, ugly approach to matching areas, but essentially we wanted to know at which point was that blue area equal to the total green area, because at that point the car and the truck have traveled the exact same distance, are at the same place. And after that point, the truck is going to be going, the truck will overtake the car because, you know, between 8 and 9 p.m., which is when they have the same distance, at that point, the truck's velocity is significantly faster than the car's velocity. Um, so that sort of hints at the idea of average value because we're thinking about the truck going at a constant value, and our average value is a constant. But this next example, I think, is a really nice illustration of what average value means. So we've got three different functions here: f of x, g of x, and h of x, and we're looking at the average value over the domain 0 to 5. And what makes what makes these problems, or these three different functions, nice is that, each of them start at 0 and end at 25. The first one is a linear equation. The next one is a quadratic equation, which is going to look something like this. And the third one is a radical. So the third one also starts at 0 and ends at 25, but its shape now looks like this: concave down. So here we have the first one is a straight line, then we have concave up, and then we have concave down. And what we want to do is find the average value over each of the following. And so we know that the average value is the integral from, well, since we're going from 0 to 5, from 0 to 5 of my function f of x dx all over 5 minus 0. So that's the total area divided by the x value. Um, so just as a reminder of, how we would actually find these, uh, the the integral, um, if, because I need to find the integral from 0 to 5 of 5x dx, and then I'm going to divide that by 5. Well, we're going to need to use our calculator for this. Um, so we go to calculator, and in our y equals, we're going to put 5x, and then we're going to integrate it. So we're going to integrate it. So go to 7. We're going to integrate it from 0 to 5. We get 62 and a half. So the average value then, um, for my first function, the average value, which I had a, yeah, here we go. The average value, so the y average would be 62 and a half over 5. Okay, in my next one, and let me stop. What I want you to do now, before I proceed and just kind of generate these integrals and figure out what the average value is, I want you to think about, which average value do you expect to be bigger? Do you expect the first one to be bigger, the second one to be bigger, or the third one to be bigger? Take a second to think about that, and try to defend your answer. Maybe pause the video. Now, now let me give you a little hint just on the first one. What is the y average, sort of, what does it mean? Well, the y average is saying this. You know, in my function, I have x and y. The y values are changing as I go up that line. And what it's saying is that over that interval, there is some average y value, that function contains some average y value, such that you know, when my, you know, at my average y value, which is right here, roughly, at that average y value, if it has that constant y value over the same interval from 0 to 5, that my red area is going to equal my blue area. In other words, if I maintain this constant average value over the same interval from 0 to 5, I will have the same amount of area underneath the curve as if I just followed my function 5x. Okay, so let's do the next problem. You know, what we're looking for graphically, we're saying that area is the integral from 0 to 5 of x squared dx. And I want to find what's the average y value over that interval. So I need to divide that area by my x values to find the average value. Well, let's go to our graphing calculator. My function is y equals x squared. Graph it. And I'm going to integrate. So second calc, I'm going to integrate from 0 to 5. And there I get 41.66. So my average value, my y average is 41.6 over 5. I've got a smaller y average than I did up here. Well, before we answer y or look at y, let's look at the next one. So in the next one, to find the y average, well, I'm going to find the total area and then divide it by the x value to find the average y. So I'm going to take the total area, which is the integral from 0 to 5 of 125x dx. I'm going to find that total area, and then I'm going to divide it by 5 minus 0 to get my average y. So go to the calculator. Hopefully you're becoming pretty familiar with these calculator functions. And we're going to do the square root of 125x. We can't really see the function, but we know that it's there. And we're going to integrate from 0 to 5. Ooh, second calc, integrate from 0 to 5. And the calculator's thinking, and we get some area 83.3. So in other words, in my first linear equation, I got my average value, which which was right in the middle. That average value is in fact 12.5. It's halfway in between 0 and 25. And then in my quadratic, my average value was smaller. It was a little bit lower. So my average value was about right there. And then in my radical function, square root x, my y value was bigger than the other two combined. Not combined, but bigger than both of the others. And then, so the question is, why does this one have a bigger average value? And intuitively, if you think about it, it grows quickly. So right away, as we trace over the function, right away, my y values get big. And so I've got big values, big y values right away. And only toward the end do my y values start slowing down. So in other words, over this interval from 0 to 5, I'm carrying bigger y values for a longer time. Whereas in my quadratic here, whereas in this quadratic, my y values stay small, they're small, they're small, they're small, and it's not till the very end that my y values get big. So I'm not, it's only for like this interval here that I've got big y values. So in other words, I don't have a lot of large y values to average out. point being, the summary being that both functions start and stop at the same point. They both start at the origin. All three of these functions started at the origin. They ended at the point 525. But because of their shape, because of the features of the graph, because of which functions got bigger faster, different functions have larger average values than the other. And just to summarize the main key point of this lesson, it's that, when we're talking about average value, not the average rate, but the average value of a function, this is a y value. The way that we compute it, over the average value of a function over the interval a to b. The way that we compute that is we integrate from a to b f of x dx, and we divide it by b over a. But, what does this mean? So graphically, let's get that picture again. What we're talking about is if we have some function from a to b, this top portion is saying, find the area. So total area. And the bottom part, it's saying divide by x. So if I take my total area, which is x times y, and I divide it by x, what I'm left off is y. And what that value gives me is my average value. It gives me an average value such that this average value over the same interval from a to b has the same area. So whether I followed my function from a to b, sweeping out that green area, and that function had changing y values, or whether I followed this constant average value over that same interval, I'm going to sweep out the same area. And this is an important idea. That's it for today.